Well, hello one and all, and welcome to our short on recursion. Now, how many ways are there for me to arrange this set of 3 cards? Let's look at it mathematically first. You could imagine that I have 3 places to put down each of these cards. I can put 1 card in each slot. Well, if I think about how many possible cards I could put in this first slot, it turns out I have 3 possible cards. I can put down any card in my set of 3. But once I put down that 1 card, once that spot is locked in, if you will, I now only have 2 possibilities for the next card. So there are only 2 possible cards I could put in this second spot. And then in this third spot, once I've put down the 2 other cards, I'm only left with 1. There's only 1 possibility for this last card here. So in terms of the sheer number of possibilities or permutations of this set of 3 cards, I could arrange them in 3 times 2 times 1 or 6 different ways. Now, if you think about an entire deck of cards, which has 52 cards, the same mathematics applies. For that first card that I could place down, there are 52 possibilities in a regular deck of cards. In the next card, though, there are 51 possibilities, and 50, then 49, then 48, and so on, all the way down to 1. And if you do this math, there are, in fact, 8 times 10 to the 67th power possibilities for arranging a deck of cards. In fact, when you shuffle a deck of cards, you are likely putting it in an order it has never been in the history of the universe. So this kind of mathematics has a name, and maybe you've seen this notation before. This reads n factorial, where n is any number. Could be 52 for 52 cards, could be 3 for 3 cards. A factorial is a way of computing how many permutations or ways of arranging unique objects there are. So if we look at the definition of a factorial, let's look at some patterns we might see. We saw here that 3 factorial was 3 times 2 times 1, or 6 possible ways of arranging 3 different objects. Well, 2 factorial is just 2 times 1. There are 2 possible ways of arranging 2 different objects. And 1 factorial here is, just by definition, 1. We know there's only 1 possible way to arrange 1 object. Now, if you look hard at this, you might notice a bit of a pattern. Certainly, we can define a factorial as the number itself times 1 less than that, times 2 less than that, times 3 less than that, and so on, all the way down to 1. But there's probably a more simple way to define what a factorial really is. In fact, if I arrange these numbers a bit more like this, you might see the pattern more clearly. 2 factorial is 2 times 1, but 1 is 1 factorial. So we could actually say that 2 factorial is 2 times 1 factorial. And once we've done this, well, it seems to me like 3 factorial is actually just 3 times 2 factorial. We're defining what a factorial is in terms of another factorial. This is what we call a recursive definition, using the solution to the problem in itself. So let's take a look here at the general form of a factorial. In fact, if we go back to using n, standing for any number, turns out that n factorial can be defined as n times the factorial of 1 less than that number. And this is a recursive definition. We're defining the solution to the problem in terms of a slightly smaller problem, but still one that is a solution to this problem as well. So let's see how we could write this in code and take advantage of this recursive definition of a factorial. Well, I'll come back here to a program I've written called factorial.py. And in this program, I have here a function called factorial. It takes in an argument that I'll call n, and I've given here the value 3. So I'm trying to find the factorial of 3. Well, we said before that we can define a factorial in terms of itself. So I'll go over here to line 2, and I'll say this function should return n times factorial n minus 1. I'm going to try to solve this problem by actually using the solution itself in a smaller form in this case. But let's take a look at what 3 would do here. 3, we'll call factorial once, n will be 3, will return 3 times the factorial of 2. Okay, so we'll call factorial again. In this case, n would be 2, and we'd call factorial where n is now 1. We'd keep going though, where n would be 1, we'd then say factorial of 0, and then we'd go again and call factorial, n would be 0, and then factorial n of -1, and I think we've gone a little bit too far. So when you're defining these recursive solutions to problems, it turns out there are not just these recursive calls, but you also need what's called a base case, a scenario where you know the answer off the bat. And for factorials, we do know this. In fact, for a factorial where I give n is equal to 1, well, I know the answer to that. If n is equal to 1, well, I know I can just return 1. No more calls to factorial are needed here. So now, in my recursive solution here, I have both what's called a base case, a scenario I know the exact answer to immediately, and I also have my recursive call where I'm trying to solve this problem by using the solution but giving it a smaller version of the problem. So let's actually visualize what's happening in code when I call a recursive function. I told you, verbally before that we're going through multiple calls to factorial, but it can be helpful to visualize exactly what those look like and how we get from all those calls to our final solution. So what I'll do here is I'll actually debug this program, which will show us the values for its variables and the number of times we call this factorial function. I'll set here a breakpoint, a place our program will stop, where we can then step through it ourselves and see visually what's happening. So I will go ahead and I will debug this program here. And you'll see on the left-hand side that I'll get access to a few windows that are helpful for me as I walk through this program. One, you'll see down below, is the call stack. This is the place where all of our function calls are going to go. When I call a function, I'm going to see it placed on top of the call stack. And when that function finishes being called, it will be taken off the top of the call stack. I can also see in this variables window the values of my variables within each call. So let's see what that looks like here. Here I am on line 8, and I'm trying to compute the result of this factorial function. Well, I want to see how this factorial function is running recursively. So I'll do what's called stepping into this function here. I'll say, I want to understand how this function is arriving at its solution. So here, we've now stepped into this first call to factorial. Notice you can see it here on the call stack up above our initial call to just the entire program itself. So here I am at the top of this factorial call, where n I actually see is equal to 3. So n is not equal to 1. This condition will not go into line 3 here and return 1. We'll instead go to our recursive call here, where I'll take 3 times the factorial of n minus 1, or 2. So let's step into this call to factorial and see what's happening here. In this case, we'll see n is equal to 2. And we'll see this new call to factorial placed on top of our call stack, just as we said would happen. Well, here, n is not equal to 1. We will not go to line 3. We'll instead go to line 5, where we'll find, again, a recursive call. We'll take 2 times factorial of 2 minus 1, or just 1. Let's step in again, and we'll see this call to factorial placed on top of our call stack. But this one, we can actually quickly resolve. N is equal to 1, so this conditional will be true. N is equal to 1, we will in fact return 1. So let's see what happens. When I return 1 from this call to factorial, notice that it goes off the top of the call stack. We've resolved that call to factorial. And now that we've done that, we can actually resolve this call very easily. We now know the result of factorial of 1. It's in fact equal to 1, so we'll just return here 2 times 1. We'll go ahead and do that. We'll resolve that call. Now we're at our initial call where we resolved factorial of 2. We can then return 3 times 2, and we're left with, at the end, a total of 6. In this case, this factorial function, given 3, has returned to us 6. So these recursive solutions to problems are a great way to build up solutions that take in some input, a smaller version of it, and then find you the answer, passing that solution back until you find the solution to your larger problem. This then was our short on recursion, and we'll see you next time.